Okay, so for those of you that don't know openhdemg, it is an open source framework developed in Python 3, in which we have integrated over time a number of tools so that you can use to visualize your EMG signals, to process your data, and eventually to do the analysis. Over time, as I said, we added a lot of things, and in the release that we just published a few days ago, we also expanded the analysis part with the decomposition and motor unit cleaning, so that now we can have an integrated framework with all the features that we need to perform advanced motor unit analysis. The project started to address a number of issues that we have in the field, and for example, the complexity that there is behind the signal processing, but also the complexity that we have in the interpretation of the data, because they can be, as we have seen before from the presentation of Francesco, extremely complex to understand. And so we are also doing a lot of dissemination activity to help you understand better the meaning of the numbers that you get as an output. Just to let you understand the dimension that the project reached at the moment, and I hope you will understand that there are good chances that inside it you will find the tools that you need, because at the moment openhdemg is composed of 171 files with 143 functions, 19 classes, and 138 class methods, for a total of 30,000 lines of Python. And over the years, we have created, modified, and deleted about 10,600 book pages, so a massive work that, just as a reference, corresponds to 15 copies of the book Dune, or 10 copies of the entire trilogy of the Lord of the Rings, okay? So that I hope you will find in it the tools that you need for your processing. And on top of this, as if it was not enough, we now also have a software. So instead of using the library to write your functions and your code in a simple way, you can also download the software and just click a number of buttons and get all the results that you will need. In today's presentation, we start with the software, because we will have a quick look at the decomposition and cleaning. And I mean, the decomposition can easily be done also from the code, but then of course, when it comes to the cleaning, we need a graphical interface, because we need to inspect the motor units, add and delete firings, and interact with the signal. So where can you find the information related to the project? Of course, the first place is our website, where you can find all the instructions, tutorials, and demonstrations. And then very important is also the GitHub repository, where there is all the code. You can learn from it, you can adjust it, and you can contribute. And if you use the project, I kindly ask you to, if you have a GitHub account, to leave a star, because it's like a like on a social media, but it's very important for developers. So this is very important for supporting the project. Then, as I said, we do a lot of dissemination activity with tutorial articles, and also with videos and presentations. So we also have a YouTube channel, and we have a discussion forum where users of the project can go and ask questions. So if you have questions about what we did today, when you try to put it in practice, you can come there, and we will try to answer you as soon as possible. So I think I've been quite fast on this part, so let's go to the practical part. As I said, we start using the software, the openhdemg software, which is a modular framework, a modular software. At the moment, we have three modules that are the blind source separation decomposition, the related cleaning, and then we have the motor unit analysis. The motor unit analysis is similar to what was previously present in the user interface of the library. Now we have improved it with a lot of more functionalities, and in a more stable framework. And of course, since it is modular, in the future we will be able to expand it based on our necessities. So when we open the decomposition, of course, everything is empty, because as a first thing, we need to select the file that we want to process. And we have a number of options for opening the files that we need. Here we have the JSON file that is present for backward compatibility, because in the past we were using this format. Very interesting, you can use a custom function, so you can develop your own function, and this allows you to load in openhdemg, so not just in the software, but in the entire framework, The custom functions will allow you to load virtually any file, so it doesn't matter what tool you are using for acquiring your signal. And then we have the openhdemg module. This is the one that we will use now. That is a data format that we have created specifically for this new release that came from a long time of studying the necessities that we have in EMG, and it's a combination of binary files and a mapping file, which has been optimized to give you a lot of speed in the loading, saving, in the processing, and a lot of flexibility. It also has a checksum that you can use to verify the integrity of the files in case you decide to share it in repositories, for example. So now we use one file that we use it for testing the decomposition, and then we will use the same file at the end of the presentation to understand what happens if you don't do decomposition and especially cleaning in a proper way, because coherence analysis is extremely sensitive to the quality of the cleaning. Of course, when we do the decomposition, we can set a number of parameters. We don't have time, unfortunately, to go into detail, but first of all, the number of iterations, which means how many times the algorithm will look for a motor unit, and then the silhouette threshold, that is the quality of the motor units that we want to find. We leave the standard parameters, so 0.9 for the silhouette. I set here 500 iterations. Sorry. We will not have time to go through them, so we'll just see very quickly what will happen. When we open a file, the first thing that we want to do before doing the decomposition is to look at the EMG signal, because if the EMG signal is problematic, then the result that we get will be necessarily wrong. In this case, we have a trapezoidal contraction, we have a very small baseline phase where there is no contraction, and then we have the signal. You can see that the baseline is very important because if there is power line interference, for example, it will manifest very clearly in the baseline, and you should remove the problematic channels from the decomposition. Fortunately, here in this example, we also have some artifacts, probably movement artifacts or contact artifacts. And when you see them, you can see the two channels at the top. When you see that there are problematic channels, these usually should be excluded from the decomposition. We can click the corresponding button on the keyboard and select them. And we can go on, and you see this file has a number of channels that are not very good. I mean, this is not a big problem. The decomposition will work even if we leave these small mistakes, but it's just to give you an example of what can be problematic and therefore is better to remove. Again, we have one here, and we have some of them around. But then we have also other cases in which, for example, a channel is not working at all. So in this case, in this case, the number 6 only contains noise, which is not useful for the decomposition, and therefore, again, we exclude it. Unfortunately, we have to go very quickly through this, but remember that cleaning channels is extremely important. Try to keep some baseline signal so that you can see the power line interference, and then try to remove all the channels that present artifacts of any kind. Then we start the decomposition. We have done a lot of work in optimizing the computational part of the decomposition, and so you can see that it is really fast. The signal is about 42 seconds, so the decomposition is running very well. And we can wait for all the 500 iterations, but now I will stop it and see what we got in these few seconds. Okay, very good. You can see here to the top left that we found 11 motor units, and the software is telling us that if we want, we can save the results. But since the software is modular, another interesting thing that we can do to make our workflow a bit faster is to transfer the result of the decomposition to another module, which of course in this case will be the cleaning. This is very convenient because at any time we can switch between one module and another and do the different things that we need. When we open the motor unit for the first time, we show the user the raw result of the decomposition. Then during the cleaning, we are using in reality a nonlinear transformation of the source to optimize the separation. And we can simply call it with a shortcut button on the keyboard. and which is, by the way, the key feature of the cleaning interface. As you can see here, there are no buttons. I mean, apart from changing the number of motor units and assigning a specific label that we can customize to the motor unit if we need it, but there is no button. So to add, delete firings, change motor units, and zoom in and zoom out, all that we do is done through the keyboard and through the mouse. Here we have, for example, a list of the shortcuts, and this was developed on purpose because once you learn the shortcuts, you will be super fast in doing the motor unit cleaning. And this, compared to previous methods, can really save a lot of time to the cleaning. And I think the best improvement that we did in this tool is the speed and quality that you can achieve during the cleaning, given the number of tools that are available. Now, let me see if I can find a more interesting motor unit, for example, for motor unit cleaning. And you see that here there are a few spikes that are discharging at very, very high frequencies. Of course, we will need to understand which one is the problematic one. We see that this is the area where there are problems, and you can see that there are three firings very close to each other. Now, there is a lot that we could say about the cleaning, how we decide which firing to remove and which to retain. Unfortunately, we don't have time, but we will, in the near future, dedicate some time to create specific tutorials for this part. But let's say we want to delete these firings here, just because we don't know which one can be problematic. And you can see that automatically the user interface will update and show how the motor unit will look if we don't have these additional firings. And if we click, for example, where is it? W. As we can see here, we can update the separation vector, and therefore we can re-estimate the source. And you see that as soon as you start manually editing your file, the discharge pattern of the motor unit will become more and more consistent. And when we do coherence analysis, we want the most consistent possible pattern. We want to have the best firing motor unit. Ideally, something like this, which is, yes, I mean, it has a bit of physiological variability, but it doesn't have holes, it doesn't have discontinuities, and so on. So, for example, we may want to add a firing gear and updating the filter and so on. Just for example here, when we do the cleaning, we should look at least two things. That is the separation between the signal, that are the firings selected with the orange dot down here, and the noise, that is instead all the remaining signal that you can see here in the baseline. What you want to see is a very easily identifiable separation between the two. If the two start overlapping, then the confidence that you have with your motor unit detection is very low, and especially for very sensitive analysis, you may be better in discarding the motor unit rather than retaining it. In addition to that, we look at the coherence that we have between the discharge pattern, the frequency, and the force profile. So, for example, here the force is very stable, while the frequency is extremely variable. When this happens, at least in healthy participants, we can assume that there has been some errors and problems in the detection of the discharge times. So we can proceed with the manual editing and try to optimize the discharge pattern that we see. Now, I'm not doing it in the best possible way, probably, but again, we won't have time to go too much into detail. And then one of the major parameters, last of the major parameters that we need to take into account when we do motor unit cleaning is, until now we just checked visually, so it was absolutely completely subjective, but it's also the silhouette threshold, which is the accuracy measure proposed by Francesco in 2016, and it goes from 0 to 1. And usually we would like to have, as you can see here to the top left where I have the cursor, we would like to have motor units that have a separation of at least 0.9. So a very strong separation between the signal and the noise cluster. And you will see that if I start to mess up with my selection, for example, I start picking signals that are close to the noise component, then the silhouette will go very low. And I mean, of course, we can see it by eye, but sometimes this is not so clear. And therefore, we have an objective measure of the quality of our motor unit detection. I think that I hope you at least understood that it's extremely important to clean motor units, and that's why we have developed a tool that really focuses on being user-friendly and providing all the information that you need to do so. And now I think we can start with the practical part in which you will see how to estimate coherence, and then at the end we see what happens if the quality of the motor units that you have detected is not good enough. So leave the stage to Elio.
Think that's right. Okay. So hi everyone. After the introduction of Francesco on the methods, a brief introduction on time domain and frequency domain methods, and then I believe that you were able to see with the Giacomo's presentation how to use the tool. So where in an integrated framework we can decompose, clean, and then the idea of let's say the last part of our workshop is to cover the estimation itself of the common inputs. So in my part, I will first talk about the time domain approach to estimate common inputs. I will not, of course, go over the theoretic part because Francesco already covered a bit. But I will try to show very practically the step-by-step parts that we need to implement or we implemented in the library to estimate these common techniques. And then after, we will see the effect on the parametrization. So how changing some parameters can affect the estimation, and we will do that directly in the codes using the library. Okay, so the first one that I will cover, and just before, let's say, cover these two main time domain techniques that I will cover, just to us to be all in the same page, for all the techniques or all the approaches we will show, always we start from the binary motor unit spike trace. And what does it mean? So regardless the approach, blind source separation or the software you use to decompose. So now, for example, if you go in our software and then you decompose the units there, the result of the decomposition commonly provides you the samples, as you can see here on the top left, the samples or the times where the units are discharged. So for example, here we have like an example of this motor unit 0 and 1 and 17, and then you see that these units discharge at the sample 3, 5, 9, and so forth. And by knowing, of course, the sampling frequency, you can have the discharge times. So the first step that this is already done, embedded in the library, is to convert this to a binary spike train, where from, for example, in this motor unit 0, you see that here, in the first and second sample, we attribute a 0 because there is no discharge, but then in the third, we put 1. So then in this way, we have a binary train with zeros and 1. 1 when the unit discharge, 0 when the unit does not discharge. Okay? And we do that basically for all the motor units identified. And at the end, we generate those signals here that are the so-called motor unit spike train signals. Okay? And in this case, we have identified 17 motor units cleaned. So I will cover here first what are the by step to calculate the so-called common drive index that, as Francesco covered, was developed in 1982 by De Luca and colleagues in a seminal work, where the steps are basically, we take the spike trains, and then the first stage is to do a smoothing of the spike trains, And we do that by a convolution. So basically, just to explain briefly, we take these spike trains and we convolve them with a window, a smoothing window that can be, for example, classically done a Rennie window, and commonly this Rennie window has 400 milliseconds. And just to have an idea, this is the equivalent to low pass filter, the discharge rates at approximately 1.8 hertz. So we are looking to the very low frequency discharge rates of the motor units. And then after this, we detrend to remove the trends in the smooth discharge rates using a high pass filter. And what we get is exactly this I'm showing you in gray. It's a very low frequency smoothed detrended discharge rate. So what is the next stage? We take all the units pair by pair, all the combinations possible, and we calculate the cross correlation between them. Is what I'm showing here, the gray signals, okay? In the x-axis, you have the legs of the cross correlation. In the y-axis, the cross correlation between the pairs. A cross correlation of 1 means that the units are very coupled in time, and -1, they are also very coupled in time, but in an opposite phase, okay? And in 0 means that they are not coupled at all. And finally, the last stage is we take commonly a very short leg, around plus minus 100 milliseconds, as done classically in the paper of De Luca in 1982, and we compute this matrix. What is this matrix is showing? On the x and y, we have the motor units, and then each square indicates the peak cross correlation in the leg plus minus 100 milliseconds. Okay? So we can see here that we have a lot of reddish colors indicating high cross correlation, and some in here for 2 units a bit blue, a bit small cross correlation between those 2 units and the rest of them. Okay? And then the common drive index at the end of the day is just an average of all these pairwise cross correlations computed at plus minus 100 milliseconds. Okay? At the end of the day, commonly it can be done or not. We also calculate a confidence level, and then we do a threshold only to consider pairwise higher than the confidence level. Okay? So just to try to check these a bit, how the parameters we chose of the smoothing window and other ones, let's go to the code, and then I will try to show you a bit how it works, or how we can very easily implement this common drive index in openhdemg library. So let me just open here. Okay, perfect. Then let me close here. Common drive. Okay. So as you can see very quickly here on the top part, here I'm just downloading one file. As Giacomo explained, we have a file that is this EMG file. And then this EMG file contains all the parameters, the signals of EMG, the motor units, discharge times, the motor units spike trains that are called in the library binary MUs firing. And it's exactly these binary MU firings that we will use in all the functions that I will and Elmira later will cover. Okay? So, let me just skip this part. Okay, so here you see that we have loaded the library as an EMG here in Python, and there is this function called common drive index. And what we just need to pass to this function is this EMG file. And using the default parameters we defined, that are exactly the ones that I just covered, we are immediately will have the results of the common drive index, okay? However, as you can see here, there are a bunch of parameters that we can change or might change depending on our purpose, okay? And I will cover basically here how changing 3 parameters can affect the estimation of the common drive index. And the first that I will cover is what we call the window curve, that is the size of the window that will do the cross correlation, because we can take the entire signal or split the signals of the smooth discharge rates in smaller windows and then do the cross correlations between these windows and average them. Okay, so just to start, the signals I show you have approximately 30 seconds, so we will do the calculations using a 5 seconds splitting windows. Okay, so I didn't cover, I will not have a lot of time to go over, but Here also we have embedded functions to plot the plots I show you in PowerPoint. So exactly the same. Okay. So let's just run this very quickly. So if I go, this one. So basically, we are loading, and then we are trying to run for 5 seconds correlations windows. And then what we will see here is first the plots of the pairwise cross correlations, as I've showed you. And on the top here, you see that we have the common drive index that in this case, remember, from -1 to 1, we have 0.6. Okay, and this is after we threshold. Okay, I will not be able to cover in details, but just for you to understand. Okay, and as you said, as I show you, in gray we have the pairwise, and in black the average across all the units. Okay, and we also can see, as I show you, this pairwise matrix very quickly, and with the values, and then so forth. So what I will do now is, you saw that the value was around 0.612, more or less. And what I will do now is to use 10 seconds windows to do the cross correlation. Okay? Yes. Yeah, no, right now I'm using the common drive index. Common drive index. Okay? And feel free, if you have any questions, just raise your hand and you can ask. So right now, then I will do now with a bit bigger, let's say, window. So, okay. And then I will run. And then in a few, please. Really good question. Until now, no. But I will cover in a few minutes that we also implement the possibility to overlap. Okay, so right now we are doing with 0 overlap, meaning that we split in no overlapping windows, but we have the possibility also to do 10, 20, 80% of overlapping. Okay, and you can see here, very interestingly, by the fact that I use a bigger window, you see that the common drive index decreased a bit from 0.62 to 0.58, okay? And you can see here, and also in the pairwise, and I will show you in a bit, you see that we have a bit more blue values, okay? And finally, just to finalize, I will use all the signal, the entire signal we have, okay? Then, by doing so, let's check. So I will use the full 30 seconds. And then you see that we decreased even more. So now it's around 0.56. And with these, what I want to highlight is that for sure, the size of the window that we use for the cross correlation or the common drive index computation affects the estimation. So a good approach that was first implemented by Francesco in 2009, commonly using windows, of course, depends on the length of your signal, but what I'm talking around 30 seconds, 5 seconds window, we reach a good compromise to have a good, like a high estimation, okay? Because of course, with the small windows, we capture these small common fluctuations instead of having a global average, okay? Great. So then, I'll just cover here another one very briefly. So now I will go over the effect of the smoothing of the discharge rate calculation. So you remember that I said that commonly we use a 400 milliseconds window. Here I will show you the effect of changing the length of this window, okay? I will show briefly using a smaller window, 150. That means that we will increase the cutoff frequency of the low pass. So we will allow more high frequencies passing. Okay, we are cutting now around 4.8 hertz. And then I will show also the other side that when we use a very much bigger window, 1 second, that we will smooth even more the discharge rates. Okay, so let me just very briefly run this stuff, and then let's hope for the best. And okay, so just a second. Yeah, please. The common drive. You mean the time of the signal, or? Yeah, so I would say that, so commonly is done around like at least 10 seconds recordings, you know, because in this way you can at least split in a bit smaller and then average across to have a bit more stable estimate rather than take just 1 second. But you could even go, I don't know if you want to comment something, no, right? Yeah, please, Francesco.
Windows, you have to be careful because if you have, for example, 1 second, you will not catch anything that is lower than 1 else. Because obviously you don't have enough center. Or soften the type of measure that you would like to have, but minutes. These the standard one from the Luca seems quite good for the product.
Yes. So, and here, what I did then, as I said, I reduced the size of the window to 150 milliseconds, allowing more frequency, so they smoothed are not so smoothed as before, and you can see that these decreased a lot, the common drive index. So now is the estimate before was around 0.62, and now is 0.28. And of course, this because by increasing or passing more frequency, we don't have these very low smoothing oscillations that are very common. That is the so-called common drive, okay? And then I will just show you the other side, that is to increase the window now to 1 second and then recalculate. Now what we are doing, we are smoothing even more. Okay, so you see now that the common drive index actually increased. And this is a natural consequence because we are compressing the frequency and we are just capturing very slow frequency fluctuations. But we need to be careful here because otherwise someone could say, Elio, so we increase a lot, so we just compress and then we just take a very high common drive. But it's a compromise because, of course, if we increase the window, we are taking very, very low frequency fluctuations. So to have an idea, a 1 second window handling means that we are low passing filter the smoothing discharge rates at 1.8 hertz. So we are looking very, very low frequency. Okay? Great. Good. So let me just come back here and so as you saw very quickly, just to summarize, so when we change the size of the correlation, this affects the common drive index. So where a small window can lead to a higher value compared with bigger windows or the entire signal. But also the duration of the smoothing affect a lot as well. And you can see here that is exactly what I show you. A very smoothing window can provide a very big like a common drive or cross correlation. Okay. And finally, I will not cover all the parameters, but just to show you is the effect of the overlapping. Okay. So in this case, what I did, I took a 10 seconds window and did without overlapping, 40% of overlapping, 80% of overlapping, and then, as expected, more overlapping we have, more stable estimate we have, and then we can capture more these small or slow frequency fluctuations, so leading to high values, okay? And as a recommendation, we believe that those parameters are a good compromise to calculate this metric, okay? Then, now, I will go to the next time domain estimation that I will cover here in my talk, that Francesco also covered at the beginning, talking about data dimensionality reduction techniques. And in the library right now, we have implemented principal component analysis, okay? And in this part, the beginning is exactly the same, where from the binary spike trains, we do the convolution with a Hanning window, we detrained it, and we obtained the train that smooth the discharge rates. But now, instead of trying to do pairwise cross-correlation, for example, the idea is to try to capture a couple of signals that can explain most of the variability of all the smooth discharge rates we have. So in this way, we can have a time varying signal that actually resembles a bit this common drive, this common oscillation across the motor units, okay? So to do so, I will not cover in details in the step-by-step. I will show you later. We have put out a preprint recently where we extensively covered all these techniques. step-by-step estimation and how they are implemented in the library. Okay, so but very briefly, after a standardization of the data, we calculate the covariance matrix. But because the data is standardized, this means that we are calculating the correlation matrix between the motor units, and then we apply the so-called eigenvalue decomposition. And what does it mean? It means that we are calculating the eigenvectors that are these low dimension projections, okay? And then we have also the eigenvalues. And the eigenvalues for each of these components indicates how much they explain in terms of variability of the smooth discharge rates. So commonly, a very standard step is we need to define how many components we need to retain, because the technique provides how many components we have in terms of motor units, okay? So to do so, we have implemented recently in a paper that we published last year, but also in the library, what we call parallel analysis. I will not go in details, but just to you to understand, we basically create a surrogated data where we shuffled the interspike intervals and we compute the eigenvalues from the surrogated data for 1,000 iterations, and we create a confidence level. And we compare these with the real data, okay? And this, for example, leads us to retain one single component, okay? Then this is the projection, and this is this low dimensional component that explains, in this case, 78% of the variability of the motor units, okay? So, very similarly, I will not, of course, go step by step here, but I already covered, like in a common drive index, but we have also this one for principal component analysis. The idea is very similar. The function is called smoothed DR PCA, where we need just to pass the EMG we are using, and then we have a bunch of the parameters. Likewise, I said that we can modify, okay? So right now, I will directly show you the effect of this parameterization, where in this first case, what we did, so we had 21 units in this case. We tried to do the PCA using 5 units from this pool on the top, then 10, and then 21. And very interestingly, you can see that in all the cases, the first low-dimensional component varies very well with those gray signals that are the smooth discharge rate of the units. What happens is that, of course, more units we include, more amplitude or more oscillatory behavior this component capture, as you can see from the top to bottom. And just to have an idea, I did the pairwise cross correlation between this component and the units, and the average values there on top in blue show very similar values, 0.86, 87, and 88. Meaning that this first low dimensional component explains around 80% of the units in all the cases in a very similar way, okay? Then, if very similar with the common drive index, smaller window, more frequency we pass, then on the top we have a more noisy low dimensional component, and more smoothing we put, more smooth is the component, and larger variance the component explained in the pool. But again, of course, is a compromise, where here also we recommend to use 400 milliseconds. And then finally, just to know, and we have implemented in the library, ordered approach to decide the number of components we need to retain, okay? There is the variance greater than 85%, for example. We can change everything, the threshold, and also the eigenvalue greater than 1. And you can see, particularly in the middle panel, that, for example, in this case, if we considered higher than 85, we would retain 3 components. And this is not the best, in our opinion, because the age and the panel AI are based on a decided threshold, but the first one is a data-driven approach to decide. So that's why it's the default one in the library. Okay? Perfect. And then, just to finalize very quickly, This is not a time domain, let's say, but I will just mention very briefly, because Francesco also covered in his presentation. We implemented also a network information framework that, again, the steps are very similar. We smooth the windows in the discharge rates in the same way, but here, instead of calculating pairwise or so, we calculate the mutual information between the pairs. That basically is a non-linear metric that we are capturing between these pairs of motor units. And as in the common drive index, we can calculate from those pairwise mutual information a mutual information matrix. Okay, here we have an example, and then we can construct from these called motor unit networks. Each circle is a motor unit, and the lines means the connection or how strongly, non-linearly, they are coupled between them, okay? And we can compute, for example, this network density that in this case was 90%, meaning a highly interconnected motor unit pool, okay? Great, so I will skip the code, so Elmira has also the time to cover the frequency domain, but just to show you, of course, more units we use, higher is the network connection, and this is natural because more units from the pool we are pulling together, and then of course they share more this mutual information between them, but also more smoothing we put in the window, also higher is the mutual information. So here again, as a compromise, we always recommend to use the entire pool and then a 400 milliseconds. Okay, great. So now I will give the word to Elmira, where she will cover the frequency domain approach, and then at the end I'm back here with Giacomo just to finalize the talk. Okay, thank you very much.
Good afternoon, everyone. For the next part of our workshop, I'm going to cover the commonality in frequency domain analysis. Let's start with the coherence. It's a step-by-step methodology, and like from decomposed motor units to the coherence spectrum, its frequency bands and their neurophysiological meaning. Okay, so far we have decomposed our signals and we got our motor units cleaned and ready for our analysis. The question is how much common synaptic input are these motor neurons receive, share, and at which frequency? This can be answered through the frequency domain analysis, through the coherence and PCI estimates. Again, as Helio already mentioned, we start with converting our signal into our spike times into the binary spike trains, and calculating our cumulative spike train into the two random half sets of the motor units. For example, here we have 18 motor units. We randomly pick 9 motor units per each CST and calculate that. And from that, we calculate our coherence based on the Welch's periodogram method, which is the estimation of the auto power spectral and cross power spectral of the signal. And we repeat this with 100 iterations. And then the pooled coherence gets estimated, and we got our coherence curve. On the x-axis, you will see the frequency on the hertz, and the y-axis is showing us the coherence between 0 and 1. Our signal gets splitted, as also Helio mentioned, into smaller windows, which gives us a more stable estimate of the coherence. So the coherence is a normalized value between 0 and 1, and if it's 1, it means that we have a very strong and stable coupling at the corresponding frequency, and we have a shared oscillatory input. When it's 0, that means that our motor units are uncoupled and are independent at that frequency, and they have a random relationship. If there is some values in between, it's interpretable regarding the frequency bands that we're going to talk about it. So what are the frequency bands of the coherence, and what do they tell us neurophysiologically? The first one is the delta band, which is between 1 to 5 Hertz, and generally attributed to descending voluntary commands responsible for force control and reflects the common drive to motor neurons during steady contractions. Next, we have our alpha band from 5 to 15 Hertz, reflect activity within spinal or subcortical circuits, including reflex pathways and proprioceptive feedback mechanism. Next is our beta band between 15 to 35 Hz and is associated with cortical contributions, particularly corticospinal drive, reflex shared oscillatory drive for common synaptic input. And lastly, we have our gamma band between 35 to 70 Hz, most prominent during dynamic or high demand contractions like fast oscillatory input. Okay, now let's talk about some important parameters, spectral parameters that can actually affect your coherence estimate. Here, I'm going to cover three more, the main important ones. The first one is the number of motor units that you are using in your analysis. As the number of motor units that you include in your coherence analysis increases, the highest gets your coherence estimate. The second one is our window duration, which is, as I mentioned at a couple of slides before, when we calculate our coherence based on the Welch's parallelogram method, we have small windows that we split our signals into that, and this affects actually the resolution of our estimate, and it's getting calculated through the 1 over the size of the window. And the third one would be overlapping these windows, and we can have different overlapping conditions based on the hypothesis or what you actually need. But the main effect of this parameter is actually the higher you go with the overlapping, the more smoothing and less variability you will get as a coherence estimate. Okay, now let's see some actual pre-recorded EMG data and see how playing with these three parameters would affect our coherence estimate. For this one, we have pre-recorded data, high-density EMG at 10% MVT. It's an isometric contraction over vastus lateralis muscle, and we got 18 motor units clean and ready for our analysis. I'm going to start with the first parameter, which is number of motor units. We keep the rest of two fixed as 1 second of window duration and half of the 50% overlap as the original paper recommendation. Now let's go to the code and see how the coherence will work for us. The same as the other functions that also Helio talked about, we have our built-in functions inside. The only thing that you need to do is you just import your EMG file inside this, and the rest of the things have been implemented by default. Here, the only thing that I'm going to play with is the number of motor units. So as I start, I'm going to put 1 motor unit per each CST per each cumulative spike train to see how that would affect our coherence estimate. Let's run it for that. It's going to repeat for 100 iteration as I mentioned before, and we will get the coherence estimate for 1 motor unit per each CST. As you can see, it's much more faster if you have already worked with MATLAB. This is much faster than that. Okay, this is the first result that we got when we just include 1 motor unit per each CST, which you can see there's almost nothing there. We barely can see anything in the other frequency band except the delta band, and the coherence itself is very low. I'm going to add 5 motor units here and see how the results will change based on that. Okay. It's clearly obvious that even adding 4 more motor units per each CST have increased our coherence estimate a lot, but we can do better. So let's add whatever we have in our data that I mentioned we had 18. So I'm going to put all of them here. and see how this changed our coherence estimate. It got much more better with higher value for the coherence, and we are going to also see soon in let's go through the presentation again. Okay, these are the three number of motor units that we just saw by running it through the code. We can see here we have also some gray curves on the background. Each of them are representing the iterations that we run for 100 iteration. You can see how fluctuated and random they are at the first case, and they are getting smoother and better, and actually like creating some shapes of the actual pool coherence, which is in orange, and it's getting much more better and more stable and accurate estimate as you enter much more motor unit into your coherence analysis. You can also see that the area under the curve for each frequency band have been dramatically increased by comparing the area under the curve values of the delta, alpha, beta, and gamma band from the first case to the last case. Now let's go to the second parameter, which is our window duration. We keep now all the motor units involved, and we go with zero overlapping for this. I will not go back to the code since we are short in time a bit, but let's assume that, as Ali also did, I will have three different window duration of 150 millisecond, 400 millisecond, and 1 second, and see how each one will affect. In the case of 150 millisecond, you can see a very broad, weak estimate of the coherence. You can barely see any information here, and based on the equation that I already mentioned, which is 1 over the size of the window duration, we have points per each 6.7 hertz, which is not that much of a really good estimate. But if we increase the time to 400 millisecond, we can already see that it developed a lot. We have a good estimate, much higher, and we have every point, like the resolution gets better by 2.5 hertz per point. Now, if we add 1 second of the window duration, we have a pretty good estimate of the coherence, much more accurate with a higher resolution, and you can see like more information from this curve. The next one is the overlapping of these windows. We keep the motor units of all of them and the window duration as 1 second. And we keep going with the zero overlapping. So in this case, you can see that the windows are not overlapping at all. We have a very fluctuated and variability in each iteration, which are the gray curves, and also the orange curve as well. By increasing the overlapping to 50% of the windows, we will get much smoother signal as a coherence estimate. And even by increasing that to 95% of overlapping, we got a pretty smooth coherence with much more like less fluctuation and less variability. Also, you can see that the coefficient of variation across the iteration in the first case is almost like 70%, then it decreases to 65, and at the end we have like 63% of variability. Based on the original literature here, our recommendation is for doing the coherence analysis, it's better to keep all your motor units for the analysis and use 1 second window duration and 50% overlapping. Next is the proportion of common input, whatever we call it, PCI index. So far, we have seen that the more we add motor units, the higher we get our coherence estimate. The idea here is calculating the pool coherence for each possible combination of CSTs, starting from 1 unit per each CST up to half of the total number of units that we got. Then we average the values for the coherence bands, and we got the PCI estimate by fitting the curve with a nonlinear model here. We have our PCI estimate on the x-axis. You can see the number of spike trains or the number of motor units, and we have the mean coherence as the estimated PCI index. Here also you can see a higher PCI means a larger portion of the motor neuron input and it's shared across the pool and indicating a stronger common drive. And the lower PCI means of the input is independent to the units. Let's go over another example of the pre-recorded HDsEMG data. This time we have recorded from TA muscle and we got 31 motor units cleaned and ready for our PCI estimates. I will shortly just show the first part of the code that like the function that we are using for this, but for the PCI, it's like taking almost like a couple of minutes to run, but I'm not going to run this, just show you the values. So as I mentioned, from 31 motor units that we got, I'm going to start with adding just 8 motor units per each CST. At the second case, I will add 20 and then the whole motor units to see how they affect our estimate. And the function and already everything is inside here. And the only thing, again, you need is just to load your EMG file. Okay, again, with the number of motor units, 1 second window duration, 0 overlap, we start and we estimate our PCI for 3 frequency bands of the delta, alpha, and beta with 8 motor units per each CST. And here you can see we have like a kind of an estimate, but with a very sharp, steep slope and not a very good estimate of the PCI index. If we increase the number of motor units, we got a better estimate, higher values for the, especially for the delta band. And okay, this one is good, but we need a good PCI estimate that reaches a saturation on the curve. That is happening when we add all the motor units inside. And you can see from comparing the curves, in the third case, we have a better estimate, especially for the delta band. And it's already like reaching a saturation and having a strong PCI estimate. Let's go to the window duration. Again, the 3 different cases of the 150 millisecond gives us a lower estimate of the PCI, as you can see. By increasing it, it gets much more better and you can have a higher value of the estimate for 400 millisecond of the window duration. And this gets even better when you have 1 second and you reach to the good estimate with a saturation on the PCI curve. For the overlapping, we take all our motor units and 1 second window duration with 0 overlapping. We already got a very good estimate here. And with 50%, you can see that it's almost the same, but kind of decreased a bit, the PCI estimate in all the 3 frequency bands. And it gets even like stays the same when we add even more overlapping to that. From whatever we saw in all these 9 cases, we can tell that the most sensitive one that we usually like do only like the PTI estimate on that is our delta band, which is more sensitive to these parameters. And we usually report that one as our PCI estimate. And as a recommendation here, we recommend to use all of your motor units, the 1 second window duration and 0 overlapping here. And I guess at this part, I will ask again Helio to cover how cleaning the motor units will actually have a very important role in your coherence or PCI estimate and all the other commonality analysis. Thank you.
So very briefly, so to conclude our part, and then I leave the word to Francesco. I'll go very briefly under these because we have these very detailed in the preprints. I'll show you in a few minutes. But this is the idea. Just we took 31 motor units. 8 of them were not fully cleaned, but it's still with a high silhouette value. So the silhouette was still higher than 0.9. Okay, but you see that of course there are a few spikes on these 8 that are not fully cleaned. And here, for comparison, we have these 8 fully cleaned. And then, just to briefly show, on the left, we have the not fully cleaned, and on the right, the cleaned, and you see that more, or just the fact that 8 were not fully from the 31 can affect quite a lot the common drive index that increase, and also the number of components retained decreased from 4 to 2, and also the variability of this component that this component explain increased quite a lot, almost let's say 20%. And the same we can observe for the coherence, that particularly in delta band was below 0.8 and passed to higher than 0.8, and the same for PCI. So this is just to say that first, we need to spend really good time on collecting good data, and all these pre-processing steps, parameterizations are really important when applying the techniques. Second, non-tonically firing units that we commonly observe that, for example, turn off or turn on or are recruited in the middle can create small fluctuations that can affect it. And finally, as I showed you briefly, be careful with the motor unit cleaning. Okay, so just to finalize, and I give the word for this last 5 minutes to Francesco. So we have this tutorial published by Giacomo that basically covered the openhdemg library and was at the, let's say, the previous release. So please, if you use the library, cite the paper, go there for further details. And recently, actually a couple of days ago, we put this preprint out where we covered all what we covered in this workshop. So estimating common synaptic inputs to spinal motor neurons from motor unit spike trains using openhdemg. Okay, so there you have all the details, you have example codes in supplementary material, and that's it. So here are all the collaborators of openhdemg. Here you have the websites where you can find further informations, the site, the GitHub, the LinkedIn, and please, if you want to keep updated with the news, the new release, the new implementation, you can just subscribe to the openhdemg mailing list, and you will get frequent updates when a new release are out.